Welcome, fellow spatial enthusiasts. Today we will be talking about the weirdness of black holes. In order to begin talking about black holes, we need to understand how they are formed. Let's say there's this massive star named Bob. Bob spends his relatively short life, a few million to a few hundred million years, fusing hydrogen and helium as you do. Later in its life, Bob fuses heavier and heavier elements. Eventually, Bob tries to fuse iron, and for a star, fusing iron is bad news. Usually fusing elements produces energy, and that usually supports the star. But when fusing iron and heavier elements, they don't produce energy, and that's a problem. But now iron core becomes inert, and as more iron gets piled on top of the core and the entire star collapses in a fraction of a second. The outer layers travel at 23% of the speed of light towards the center. That's fast. The speed of light is 300 million meters per second. For comparison, the average stride length for a 6-foot person is 0.7 meters. For easy math, we'll round up to 1 meter. 23% of the speed of light is 69 million. And that's like saying you're taking 69 million steps in 1 second. Two paths after the core collapse can result. The first path that can result is if this iron core is not massive enough to overcome neutron degeneracy pressure at 2.16 solar masses. The core is halted. It does not collapse any further. It's a full stop. The brakes have been slammed. The outer layers again are booking it at 23% the speed of light. The core will not budge at this point. The result is that the outer layers bounce off of the core extremely violently. This is a Type 2 supernova explosion. We can simulate this same mechanism with a demonstration on Earth. I've mentioned that the core is supported by this thing called neutron degeneracy pressure, which is some quantum physics stuff that we'll get into in another video. What we need to know for this video is just that this results in an extremely dense neutron star, a collection of matter that's at around 1.5 solar masses condensed into a radius of 15 kilometers, about the size of a city. There's a lot of other weirdness that neutron stars have, which we will save for another video. But we came to learn about black holes. I'm getting to that. The current estimate for the maximum mass of a neutron star is 2.16 solar masses. Some of the ejected material from a supernova explosion may fall back onto the neutron core. If the total mass of the neutron core exceeds 2.16 solar masses, it collapses even further. No known force at this point can stop the core from collapsing, and all the matter is condensed into a single point called a singularity. The second way a black hole can form is simply when the iron core is above 2.16 solar masses before the collapse, and the core collapses directly into a black hole, failing to create a supernova explosion at all. Alright, so there's this smart guy named Albert Einstein. I'm not sure if you've heard of him. Some of his absolute best contributions to physics lie in his theory of relativity. Special relativity, which says the speed of light, is constant. Nothing is allowed to exceed the speed of light. General relativity, cool kids call it GR. General relativity means that gravity is not a force, but a warping of space-time, the Schwarzschild radius of a black hole. This is the distance from the center of a given mass at which the escape velocity is greater than c, which, as we know, is a problem. Nothing can go faster than the speed of light. Alright, so we have a few numbers and letters randomly strewn across the board. So from here, we want to derive the escape velocity, and we have the absolute value of this gravitational potential energy, Gmm over r. G is the gravitational constant, which is 6.67 times 10 to the negative 11 meters cubed per kilogram second squared. So we have gravitational potential energy. We want the kinetic energy to be greater than the magnitude of the gravitational potential energy. So we put absolute value signs around both of them. So deriving that, we find that v, escape velocity v, equals square root of 2gm over r. And what we want to do with this is find the event horizon, the source shell radius. And in order to do this, we just need to plug in c, speed of light, for v. Then solving for rs, we find that rs equals 2gm over c squared. Alright, now we have some more weird equations on the board. This is the gravitational redshift equation. Lambda 2 and lambda 1 are wavelengths. What we want to do is just have R2 go to infinity. So we're comparing the wavelength from an observer who's not in a gravitational field. So we just have 1 over 1 minus 2gm over r1 c squared. And what we want to do with this is substitute rs for r1. Now, substituting that in, we have 1 over 1 minus that quantity. And so we have 1 over 1 minus 1 square rooted, I guess. And that's 1 over 0. And for our purposes, we're going to call this infinity. Now, that may sound blasphemous or illegal. Don't burn me. But it makes more sense when we think of it like this. What we have on the other side is energy of a photon, which is both a particle and a wave, which we will get to in another video. That's some quantum physics stuff. But anyway, energy of a photon is hc over lambda. H is just Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. Substituting in this result we got for lambda 2, which is infinity, we get hc over infinity. Any number over infinity is going to be 0. That just means that luminosity equals 0. So now we have the time dilation equation, which is literally the same equation with just t2 and t1, which are times. So all this remains the same. We want to do the same thing with R2, compare it to something that's not in a gravitational field. Also, excuse this entire side of white space. Maybe we'll put a picture of something in there. But T2 over T1 equals 1 over 1 minus 2gm over r1c squared. And what we want to do still is add the rs, or substitute rs in for r1. And we get the same result, 1 over 0. T2 equals 1 over 0, which is still illegal. Alright, you may be saying, okay, you just threw some random math. What does this mean? What is all this time dilation nonsense? So glad you asked. In order to find out the answer to your question, you volunteered to fall into a black hole. Don't do this, by the way. There are better ways to answer your questions, like watching this video. But let's say you're falling into a black hole, and you're holding a giant clock. This clock means nothing to you, but you happen to bring along a friend, which I suppose wouldn't be your friend, considering they're just watching you fall into a black hole. But whatever. Let's say this person is watching you from far away, eating popcorn. Maybe they're taking notes. They watch this giant clock you're holding, and what they see is the time on your clock ticking slower and slower until you reach the event horizon. At that point, for an instant, the time is completely stopped, but in that same instant, you are gone. But let's consider the other side. You're still falling into a big black hole, but this time, your friend isn't eating popcorn or taking notes. He's just holding a giant clock, as one does. And instead of screaming, you decided to do something constructive and watch this clock as you fall into a black hole. Now what you see when you fall into the black hole is the time on that clock ticking faster and faster as you get closer to the event horizon. Now, hear this. Once you are at the event horizon, all time passes at once. Your birth, your very imminent death, the beginning of the universe, the end of the universe, all at once. Don't think about that too hard, it'll hurt your brain. Thus far, we've discussed stellar mass black holes, which are around 3 to 100 solar masses. There are two other types of black holes. One being supermassive black holes, which we know for a fact exist. Supermassive black holes are generally found in the core of every major galaxy. That means our galaxy, the Milky Way, has one. So does the Andromeda galaxy, and a bunch of other galaxies. I'm not going to name all of them. There are a lot. The middle ground is the intermediate mass black holes. The range of masses for intermediate mass black holes is 100 solar masses all the way to 100,000 solar masses, which is a huge range, mind you, but we have yet to find any definitive examples. The very few examples we have found about intermediate mass black holes are very controversial. In other words, we have no idea if they exist. So how do we know that black holes in general exist? Well, first, we can see gravitational effects of black holes. If we see an object gravitationally affected by some unidentified force, it's safe to say that there's probably something there, i.e., a black hole. And confirming that black holes exist, we have taken our first picture of a black hole in 2019. This black hole is a supermassive black hole found in the galaxy M87 and is 6.5 billion solar masses. This is the type of black hole you will want to fall into for reasons I will explain with more math. What you see now here is a random weird equation on the board, and that the equation is describing tidal forces, or tidal accelerations, I suppose. Acceleration is proportional to force, given by this formula that some obscure guy named Isaac Newton proposed. So going through this equation, dg is the difference in gravitational acceleration, and r cubed is the distance from the center of whatever object. And immediately what we see is that smaller objects and bigger masses have bigger tidal accelerations. And again, we're talking about black holes here. So naturally what we want to do is talk about the Schwarzschild radius at the event horizon. So we're substituting rs for r. Rs, we remember, is 2gm over c squared. And once we substitute that in, we end up getting negative c to the 6 over 4g squared m squared times tr. So now I want to discuss the orders of magnitude here. The typical mass of a black hole of this type, a stellar mass black hole, will be around 10 to the 30 kilograms. So 10 to the 48 over 10 to the 22 is 10 to the 70, and then 10 to the 70 over 10 to the 60 is 10 to the 10. But we're going to compare that to the tidal forces felt on Earth. dr, still 2 meters, and then this is the gravitational constant, and then times 6 times 10 to the 24, which is the mass of the Earth, about. And then the radius of the Earth in meters is 6.371 times 10 to the 6, and then we're cubing that. So we end up getting 10 to the negative 5, or because there's that negative sign, negative 10 to the negative 5. And as you can see, there's a large difference. This is 10 billion, but this is essentially zero compared to this. This is a whole 10 to the 15 orders of magnitude bigger than what we feel on Earth. 10 to the 15 is, I think, a quadrillion? I don't know. Oh, but that's a lot. And also, gravitational acceleration, the normal gravitational acceleration that we feel on Earth is, again, negative 9.81 meters per second squared. And that's on the magnitude of 10 to the 1. So this is a billion G's of acceleration, which is immense. So don't fall into a black hole. Now, let's say the first time you fell into a black hole, you broke the laws of physics and escaped that black hole through jumping really hard and reaching velocity faster than the speed of light. As a consequence of you breaking the laws, the space physics police catch you and throw you into a black hole as punishment. They obviously haven't learned anything if they're just throwing you into a black hole again, right? See, you would think that, but they all have PhDs in physics, so naturally, they know about tidal forces. This time, they find a black hole of a much smaller radius, try a stellar mass black hole, and they ensure that they throw you in the black hole feet first. Because of the immense tidal forces that you'll now be experiencing, you will start to stretch. Now, at first, this may feel like a stretch you might go to the spa for, but eventually you keep stretching to a point where you're in pain, and you keep stretching until your spine that's usually in one piece turns into a spine of two pieces. You snap in two. As you keep falling, each piece of you snaps into two more pieces and two more pieces until your atoms split. At this point, the physics police moonwalk away. But having broken the laws of physics once before, you have no problem doing it again. And so you reassemble and just leave the black hole unscathed. This process holds the title for the absolute best name in all of astronomy. The process is known as spaghettification. Spaghettification. If there's a better term, I've never heard it. But don't do it, it's painful. Suppose we should end on a nicer note than spaghettification. I don't know. Black hole pictures look cool. At least the artist renditions of them. They make good posters, I suppose. Go buy some black hole posters, and I will see you later. And always remember to keep wondering.